All right, so we will continue to introduce some of the basic technique for network and I/O. So network actually is very, very important, sometimes more than computation. Because as I mentioned, um, communication cost is the main bottleneck for almost all the payroll programs. Because as we all know, network is generally slower than the CPU, right? And also, however, for payroll computation, payroll program, more or less you need to communicate, right? And sometimes you need to communicate frequently. Your performance can be throttled by those communication time. And also for payroll computation, sometimes you not only need to communicate with other processes, you also need to synchronize with other processes, right? Because you have data consistency problem, you have those um, synchronization issues. So you are forced to synchronize or communicate. Otherwise, the result may not be correct. Okay? Especially those synchronizations sometimes require blocking code. Means you have to wait until a certain process to reach certain point of their program. So all you can do is just wait until you are allowed to continue your program. Okay. So all those activity and behaviors are very time consuming, and sometimes you cannot just avoid it by your network. It cannot be solved by network bandwidth because it's about when you can continue to run, not just how fast you transfer your data or message alone. So all those are counted as communication overhead, okay, because it's those are the activities you need to do between processes, right? But from the infrastructure, the hardware, or the network point of view, prospect, what you can do and what need to consider are not just performance sometimes, but also cost, resilience, and scalability. So we will talk about each of those factors later. Okay. But for networking, it's also complicated because you have several layers, right? From the hard network device you use at the bottom, right, to the network topology. What's the routing, right, on top of those network device? To the on the above your application in terms of what's the network or the communication protocol you use, and what's the communication pattern of your program. For this course and for you as a programmer, basically the thing you definitely need to do to optimize is the communication pattern. For example, in your homework, you will try to use for example non-blocking code, or try to to avoid those synchronization overhead, or you will try to reduce the amount of data you need to communicate, right? Or reduce the number of communication in your program in order to minimize the communication time. And also probably you can configure your library to choose a better network protocol. But for the computer system itself, then those computer system will decide what's the network topology and the network device for you. For network device, this is the you have different cable, different switch, adapter, network equipment you can choose from. And the infinite band we mentioned, right, is the technique that is a better network device to provide high bandwidth and low latency communication for our system. And above that is the network topology. And the network topology is important because we will see depends on how you route the packet. It can affect not performance, resiliency, all the factors we mentioned. They are all affected and determined by how you route the packet in your network. So network routing is definitely one of the most important problem for networking field, as well as for high performance and distributed computing field, because networking is part of it. Okay. So let's first look at the network topology. So the network topology, there are, of course, there are all kinds of topology. Some of you probably already heard, but here we will we'll introduce a few network topology to explain how those topology can affect performance, resiliency, and scalability, etc. Okay. So the simplest network topology is a linear array, right? It's very simple. You just connect all the nodes, the computers in a single linear line. And so the way we can analyze the topology is to analyze its diameter, bisection, number of links, and degree. And as you can see, each of those metrics indicate the degree of performance, that's latency, right? And resiliency. What's bisection? Bisection means how many lines do you need to cut in order to bisect the topology, the network. If you can bisect the topology, the network, that means the network fails, right? Because if you bisect if you can bisect the network to two parts, that means there's no way for you to communicate between the two nodes in different part. So you basically cannot communicate anymore. So bisection is the minimum value you can tolerate, basically. So this number, of course, is higher the better. And the latency, of course, is the lower the better. Okay. And specific, the latency here is measured by the number of hop in your communication. And third is the number of links. It represents the cost in some way, because more links means more hardware device, more expenses, right? So how many links do you need to form this topology in order to connect the given number of nodes, right? Which is represented by P in here, by the way. Okay, so P is the number of nodes, okay, in the graph, in the network. And finally, the degree. The degree means for each node, how many network port it needs to form the topology, right? So for example, for the linear array below, you can see each node at least had to have two hops, right? Two ports, right? Connect to their neighbors, right? One on the left, the other on the left. So this number will be lower the better, okay? Because you can imagine if you have thousands of machines, then if your degree is proportion to it, that means you need to have 1,000 port on each node as well. But as a matter of fact, there's no such server exists, right? There's no a single server can have 1,000 network adapter card plug on it, install on it. So in some way, this value indicate your scalability, means how large a system you can build on it. Okay? And for linear array, you can see the diameter is very bad, right? Because for P number of server, you need, the worst case, you need P-1 hops to communicate to the rightmost one and leftmost one. So it's a very long latency delay. For bisection, the resiliency is also very bad because any single line, is broken, then your network is down. Okay. For the cost, in terms of the cost, it's basically optimum, right? Because there's no any other topology exists to connect P machine with even fewer number of links than P-1. So of course, it's a cheapest solution. And for scalability, it's very good as well because it's a constant here. 2 is not just example. 2 is a constant. So no matter how many servers you have, each server always only needs 2 ports. So of course, it's scaled very well, and it's even a constant. So you can see a simple topology like linear array also has its strengths and its weakness. So in certain environment, in certain case, people actually do like to use a linear array. Especially, for example, of course, the linear array can be easily approved by connected the leftmost node to the rightmost the rightmost node, right, to form a ring, right, like we show the second row here. So it's an easy way to just increase the cost a little bit, but you double the bisection and half of the diameter. So ring is actually a quite commonly seen topology for a small scale environment. For example, like in your dormitory, you probably use a ring topology, right, to connect the just the PC and your laptop in your dormitory. Okay. The third topology we would like to introduce is tree. We don't have a plot over here, but I guess everyone can imagine that, right? So tree is just the tree structure we are all familiar with, the data structure we always look, we always see. So as you all know, the diameter for the tree should be 2 times log of P, right? Because you have to, the worst case, you have to go through the node, the root, right, all the way up and then all the way down. Okay. And but still, right, it's much better than ring or the linear array. And for bisection, unfortunately, it's also very bad because any link broken, then you have a bisection. Okay. And in terms of the number of links, of course, it's higher than the linear, but consider the latency improvement you get. So people, actually in some case, when the larger scale case, people actually prefer tree more. And finally, is the degree. So you have to connect to your parent, and you have to connect to your children. And here, assuming the tree structure we have is the simplest, the binary tree. So you only have 2 children at a time. So the degree is only 3. And of course, as you can imagine, there are variation of the tree structure, right? So you can twist the tree structure to gain better resiliency, or to with the cost, with the higher cost, or you can further improve your latency, etc. Okay. But one of the famous tree structure I didn't show here, but I can briefly describe, is called the fat tree. Okay, so the fat tree is that he tried to solve the bandwidth problem. Actually, the bandwidth problem is not shown here. The bandwidth problem, it means that the bandwidth, the network link, the bandwidth of the network link is more oversubscribed at the higher level when we get closer to the root, right? Because you can imagine everyone need to go through the route to the other side. So as the traffic goes toward the route, then the amount of traffic toward the route will increasing, right? It will increase and with more than the traffic you need to handle, at the leaf. So because the number of edge you have on the on the top is less, right? It's fewer than the number of edge we have at the bottom, right? So that means you will more easily suffer from bandwidth congestion to the link on the top. Okay, so for factory, if you go up one level, he will add additional link to it. So basically, the purpose is to give you more bandwidth. The link will become wider, or you have more bandwidth as you goes toward the route. Okay, so make sure the bandwidth is not oversubscribed, even if you are at the top of the root node. Okay, so that's the factory. And in addition, because you add more link to the root, so those links also provide better resiliency. So even if one link goes down, then you have other links to replace, right? So you will lose the bandwidth, but you don't lose the connection. So factory is one of the most commonly seen tree structure for cluster and supercomputer. Okay? All right. Of course, there are a lot of more interesting topology exists. And another famous one is the mesh, is the one we show below. So for mesh, you can see it can have multiple dimensions. And the one we see here is two-dimensional mesh, because you can see it's a two-dimensional, right? And mesh means that in this dimension, you are connected to the one on the top, the right, your neighbor, on the left side, the right side, and you're up and down. Okay, so this is a mesh. Okay, and as you can see, the diameter, right, is square root of p minus 1 times 2. Of course, that's the length of your dimension, right? And you have the worst case is when you travel from, for example, the top left to the bottom right, right? And the bisection, you can see you have to cut basically all the all the neighbors, right? So this is square of p. Okay, and the links, I guess you can compute it, right? The number shows here definitely correct. So you can see the downside of mesh is you require even more costs, right? And the greatest benefit of mesh is the resiliency. Okay, and resiliency actually also sometimes reflect the load balancing, because if you have more route, right, then that means you can balance your traffic across multiple paths. So with the help of your routing protocol, usually you can fully utilize all those routes. So you can have you can balance your load better. So more people. So usually we do want to have better higher value for bisections. Okay, and in terms of degree, it's more, but still it's a constant. So it's also so as you can see, actually for large scale system, the most important thing is scalability, because if you don't have scalability, then it doesn't scale. So that means it's not practical. It's not feasible solution at all. So the most important thing, the most important constraint limitation is scalability. Usually it definitely should be a constant. Okay? So we can keep increasing the scale of our system by adding more nodes. Okay? All right, and this is example for 2D mesh. So you can imagine for 3D, 4D, you can further extend it. So to get better resiliency and better latency, of course with the cost, with a higher cost and slightly increased scalability. All right, and finally is the torus and hybrid cube. Torus is basically a variation of mesh by connecting just like how we extend linear array to ring, right? We can the same way to extend mesh to torus by connect the leftmost to the rightmost, the topmost to the bottom one, to make it become a ring. So that's what we call the torus. Okay. Right, and finally is the hybrid cube. So this is how a hybrid cube looks like. So a hybrid cube basically is, as you can see, for every node, we can use a binary form to label the nodes. And also the hybrid cube can be multi-dimension. And the dimension referring to the number of bits you use to represent the graph. So actually for hybrid cube, the number of dimension depends on the number of nodes, right? Because you need to have the matching number of bits to represent the node. Okay, and the connection is formed between the nodes when they have a single bit of differences. For example, 1111, right? You will connect to 1110. Let me find it right here, right? And it will connect to 1101 right here, and 1011, as well as 0111 right here, right? So the dimension also represent the number of neighbors for each node. And the most important, the biggest strength of hybrid cube, as you can see, is the diameter. So hybrid cube is a topology that can provide the highest performance, as you can imagine, compared all other commonly seen topology. And it can also has the highest bisection, right? The best resiliency and the easiest load balancing property. Okay, but the cost is really high, much higher than all other topology, right? And most importantly is the degree. Unfortunately, for hybrid cube, its degree is is a function of the size, the scale, right? The P over here. So if your system grows, your degree will just also keep increasing. So this topology can only fit for a really small degree of a system, probably under number of tens, okay, tens or 20s nodes, that kind of scale. So hybrid queue normally don't sing in the network switch. We usually don't have this kind of a network topology. But for a single chip or a multi-core processor, or even a network, or even a many-core processor, in that scale, then we will see this kind of a interconnection network. So it's usually a on-chip network, or it's a simple it's a routing within a single switch. Okay, so usually is within a computing device or chip, in short, not in the scale of a networking system. Okay? But still, it's a topology, and this kind of a network topology issue definitely not just at the level of computer nodes. It can also be in a level of processing unit or core. So we also know the same concept and the same design. All right. So hyperQ is really we usually don't see in a supercomputer at the networking level, but within a single chip. So for supercomputer, right? Of course, networking important and topology is critical. So you will see for every supercomputer, they usually have their own unique network topology. And the K machine is a good example. So it once was a number 5 machine in the world, and his topology is very interesting. It's you can see it's a 6-dimension mesh and torus. So I'm not going to introduce the detail. It's similar like the torus and the mesh we introduced, but of course here is even more complicated. And if you are interested, I strongly recommend you to watch this video, a very short video, just a few minutes, but it will tell you exactly how this topology looks like, and you will see the main design objectives. It's not just to ensure you have small dimension or small latency in across the whole supercomputers, with more than 80,000 nodes, but also he wants to provide multiple path routing so you can be more resilient to the value and better balance the traffic. That's why they designed this. They use this six-dimensional torus network topology. All right. Okay. So the last topology I also want to introduce is it's a more recently developed or proposed topology, which has been used in some of the latest supercomputer. And this topology is called the Dragonfly. As you might know, dragonfly is kind of an insect, right? The reason this topology is called dragonfly because it looks like the dragonfly, especially the wing of the dragonfly. So as you all know, a dragonfly is like like a character T, right? So that means if you are very close, okay, so if the machine are very close, for example, they are in the same rack or the nearest rack, then they have more connection between it. Just like the wing of the dragonfly is very dense, you have see many connection lines within it. But at the same time, dragonfly has a long tail, right? So this long the purpose is like just like highway, right? If local, we have those subway, right? We have subway, we have those local transportation, bus, all kinds of connections. But if you are very long, then far away, long distance, then we have high speed network. We have high speed train, right? Or we have highway, right? So if you want to route it to a node that's on the other side of the supercomputer, then he will be routed through those long link. And when you reach a node at that region, then you can use the local close connected links to forward it to your final destination. Okay. So basically, that's a topology designed to make sure you have um, very low latency across the whole system. At the same time, you don't need to fully connect it every single server in the system. So you can reduce the cost and you can reduce the degree of each node and have a better scalability. Okay. So that's the concept. Okay. The concept easy to imagine, but why it doesn't get realized until recently? Because of the technology. The technology in terms of two things. One is that because if you want to have this long cable, it's not that easy. Because the longer the cable is, the higher noise and the lower or higher packet drop rate could incur. So if it's too long in the past, there's a limit. It doesn't allow you to have a network cable that long. So that's the first limitation. The second limitation is the scalability of our network switch. So just like the plot we show on the right side, you can see there are so many links if you are in a closed region. And that means you need more ports and switch, right? Then, in a single switch, you need to connect it to more machine. And before, the number of port for a switch, maybe just 100, but now we can have even more. So, so we can ensure we can, fully connected all the, for example, all the nodes on a single rack. So this topology only works because of the advance of those hardware equipment allow us to do that. Okay. This is a more recent topology that has been used in those supercomputers. Okay. Right. So that's it for the network topology part. So you can see that still it's an interesting problem, how to design those topology, and not just from the mathematic point of view, but you actually sometimes you need to have those hardware support to enable you to realize those routing in practice in the real world. All right. So next technology we will talk about is the infinite band, as I mentioned, as I just mentioned it, right? So you can see from top 500 list, most of the supercomputers are already using infinite band. And this infinite band technology is mostly provided by a company called Mellanox. This is a very famous company because of the infinite band solution. And if you watch the news, it just get bought by NVIDIA. Why is that? Why NVIDIA want to buy Mellanox? Because just as we mentioned, the computing power today grows very fast. Like GPU, CPU, those processor, they can have their computing capability increase in a very fast pace. However, you need to feed the data to it, right? So eventually you have to leave the car, leave the device. And the way you can provide, right, feed data into it is through the network. You need high bandwidth. Otherwise, the performance will be stuck at the network part. You never be able to get to your processor. So that's why they see the importance, and they buy the company, and they want to provide even better integrated solution, so you can fully utilize the computing power. Right, and the plot below, you can see that the difference between infinite band and Ethernet in terms of their performance. Okay, so it's a huge gap. So that's why infinite band is almost the necessary networking for real high performance computing. And as a matter of fact, the computing cluster you use in this course also has infinite band. The reason is of course so that we want to be able to get better scalability and performance out of your program, right? So your performance will not be stuck at the networking part. So this is right, another plot. We mentioned from the top 500. So obviously, there are more and more computer system using infinite band. And of course, this plot is not this year, but a few years back. So that's why you can still see the cross between the two technology, but it already happened many years ago. So today, basically, everybody choose infinite band if you have the money, right? Because it's very cost expensive. Okay. So let's just talk briefly. Why this infinite band can be so fast? And it can be so fast for two reasons, for two reasons. The first one is, as we all know, network consists of many layers, right? Strictly speaking, probably 7 layers. And there's a reason for that, because you want to be more general. You can adapt different protocol So you can communicate between different devices and network, network device. So you can hide those, um, differences in each layer. Okay, but unfortunately, the price is between layers. They are different processes, so they have to copy your data layer by layer and package, unpackage, and all those things happen on the inside the operating system. So all those things takes time. And for infinite band, you use the technique instead of rely on the operating system. You use the RDMA technique. The RDMA technique, if you took the operating system course, you might learn what's DMA already, right? Direct memory access. So basically that means the memory, the content can be directly accessed by the hardware without going through the operating system at all. Okay, so that means we can bypass the operating system, bypass the network layers when we need to transfer the data, or transfer your packet. So packet, itself is just a memory copy, right? So we want to reduce the number of memory copy, along the way. So that's why it can be much faster because it bypassed the operating system, it use hardware, and he doesn't need to go through those 7 layers of processing. Okay, just as the figure we show over here. Okay, the second reason is the traditional TCP protocol is the best effort transfer protocol. Basically, that means because the network channel is shared by many devices, so you cannot have you might have a conflict when those devices try to throw their packet on the network channel to transport the packet. So you might have a conflict happen when you do the transportation. And best effort means that if you want to send something, you just throw on the network channel. If you unfortunately it get conflict, bump to other packet, then you just resend again. So that's best effort. So if the load is light, right? If not many people using the bandwidth, then or the channel, or your bandwidth is large enough, then you might have a lower conflict probability. So it could be efficient. But for high performance computing, basically we're assuming there are always traffic exist. So the loading is always high. So you are more easily to run into those confliction. Okay? Then what happens? You have to resend the packet, and then of course the bandwidth is wasted. Okay, so it cannot fully utilize the network bandwidth. But for the infinite band, its protocol is reservation based. So you will reserve the bandwidth before you send the packet. And of course, that means the network adapter card will actually have their own control plan, control communication to make sure they have those reservation exist before you send the packet. And all those, of course, is done by the hardware, done by the adapter, or done by the network switch. Okay, but after they reserve the bandwidth, then you can send it the traffic without resend it again. So that's why you can better plan and utilize the network bandwidth. Right. So so this is the table summarize the differences. The main difference is the 2 things I mentioned. The delivery protocol, the control protocol is completely different. One's best effort, the other is actually have a flow control, at the lowest level, not just at the flow control level. Okay, and done by hardware as well. Okay, and also the RDMA technology, infinite band from the start is rely or use the RDMA technique. But for the Ethernet, it's not. But it doesn't mean it cannot use RDMA. There's no confliction to it. So in fact, Ethernet right now, there are research and blueprint or roadmap design to support RDMA or use RDMA in the Ethernet protocol. However, it's less mature and still is is a step behind the infinite band. Okay? So at the end, the most important result is in terms of the latency, infinite band can be much shorter than Ethernet. And in terms of the bandwidth and the throughput, infinite are is also much better than the Ethernet. The only limitation for infinite band is still the length of the cable, right? Just like we mentioned for the cable inside a supercomputer. So the infinite band, however, 4 kilometers is pretty long already, right? So infinite band can be used for supercomputer without any issue. But at the same time, it probably cannot be extended to the whole internet, the whole world. Okay. And also the cost is extremely high, right? So you will probably only see it for the supercomputer or some high performance driven computer system. All right. So that's for the networking. Okay. Um, any questions? Okay, we have a few minutes left, so we will finish the storage part. So the last one is I/O and the storage. So when we talk about performance, people usually first look at the computation part, right? Do you use GPU or not, right? Have you, parallelized your code? Those kind of questions. But as we introduce, you will find that after computation, networking is important, right? Because that's the performance bottleneck, and that's why it cannot fully utilize your computing power. But lastly, even less people talk about storage and I/O when we talk about parallel computing, um, because as a matter of fact, no, we don't talk that much, but doesn't mean it's not important. In fact, it's even worse, right? Because I/O usually is even slower than the network. So that means it's even no, no, a bigger performance bottleneck you will face. Okay, but why we talk less? Mostly because usually we will basically preload the data, right, to the memory or some other cache or memory system, so we can avoid the I/O. Or when we do the computation, we will find a way to try to exclude the I/O time. Otherwise, of course, it will be easily slowed down by the I/O, the I/O time. Okay, so but eventually, unavoidably, right? Sometimes you still need to access the data from the storage. So optimize the I/O, of course, is still one of the most important topic in high performance computing. In fact, remember we talked about the access scale computing, right? For access scale computing, the storage is the big part of it. Okay, so um, because in that speed, that means you have to have multiple hierarchical layer of storage exist, including those memory, in order to to prevent this I/O slow down the computation. So of course, those kind of solutions not just for the storage device alone. No, it even include the the memory management and the I/O buffer management um, as well. Okay, all right. So that's as I said, right? The storage when we talk about the I/O, it's not just the storage system; it's the whole I/O pass, right, from the storage system all the way to your computing device, the register of your inside your computing unit. So this whole pass is I/O, right? So the optimization is not just the storage; it's also how you manage your memory, right? How you manage your cache, right? Where to cache or what content should be cached. All of those questions. And for I/O, of course, one of the way to improve it is to invent, right, new storage device or I/O device that provide faster access time or larger storage space. But unfortunately, usually those two things are right, contradict to each other, goes the other way. So if you have a larger storage space, usually means you have slower access time. So that's why we always see this hierarchy showing here. And when some new device, storage device, get invented, then the question usually is, where should we put it in this hierarchy structure, right? Which level should it be? And how we manage the data in the storage device. So the non-volatile memory is a very good example in the recent year, right? So SSD, everybody knows, already widely adapted in your personal computer and laptop, right? So he can provide much better access time than the traditional disk. But usually we cannot store all the data to there, right? Because it's more expensive. Okay? And another interesting is the non-volatile memory actually is not just SSD. It can also be used as a memory. So the interesting part is in the past, in our system architecture, we always assuming memory is something that is not persistent, right? If you are powered down, then you lost the data. But non-volatile memory is interesting because even you power down, without the power, your data remain. It's a good thing, but sometimes it can be a bad thing as well. The good thing is, sounds like it can be more resilient. It can be used to, it can be some fault tolerance solution, right? But the bad thing at the same time is because all our software, when we develop and design, assuming the memory will be reset after rebooting. But if it's not, then this is a different assumption and some of the design need to be changed. Otherwise, he may read an inconsistent state from the memory. So it's not always a good thing as a matter of fact, okay? All right, so, but anyway, non-volatile memory is a very interesting topic today still, okay? And another topic for I/O optimization is the payroll file system. This related to our course as well, because of course your data is stored in a file system. And how we can make a file system faster, right? The easiest way is use those payroll file system. A file system that consists of multiple servers or storage node. And because between storage node and your compute node, you can have individual network connection. So you can use more link, install more links to provide or to get more higher bandwidth. So you can transfer more data at the same time, right? And when we talk about our first payroll programming language, MPI, we will also introduce MPI I/O. So at that time, you will see how we can use MPI I/O to communicate to a payroll file system. Okay? Below is just the structure of the payroll file system. The important thing is just you will see there are many OST. So it's a storage. It's a storage target, object storage target. You can think it as a storage node. So you actually have multiple storage node. Okay, and to communicate with C is the compute node. right? This is probably the last slide, so I will finish this before we finish today's class very quickly. Okay, so for parallel file system, one of the very interesting technique just recently proposed in maybe 2 or 3 years is called the burst buffering. Okay, so the burst buffering, the problem you try to solve is that the I/O traffic is usually very bursty, not stable. Means sometimes you have a lot of I/O and sometimes you don't, because I/O is time consuming. So you can imagine most of the program try to compute as much as they can and only store the data when all the computation is done. And they store the data at once, dump everything to the storage system. So it's very bursty. And the problem for that is the network bandwidth we need to reserve or we need to preserve between the compute node and the storage node, just like between the compute node and the parallel file system, right? If we want to make sure the I/O perform well, sounds like we have to optimize for the peak load, right? But unfortunately, the peak is really high, so that means the cost is very high, but the utilization is very low because most of the time it's idle, so it's not very ideal. So what we need is a buffer. As we all know, buffer is a solution that change the speed of the data transfer. So what happened is the burst buffer is it's just a memory installed on some server, sits between your compute node and your storage node. And the data will first store on the memory buffer of those storage on those on those nodes, and then transfer to the storage node. So if you write many data at once, it will actually just write it to the memory of those burst buffer. So it reduces the latency because you only write it to buffer, not the I/O device, right? So the I/O time will be faster. And after that, the burst buffer will slowly and gradually write the content or write the data in the memory to the storage node. So you can write it, no, you don't need to write it immediately, but you can write it over a long period of time. So the demand will become smooth, stable, right? And the peak demand will be much lower. So we don't need to build or no, we don't need to have those high bandwidth link between the storage node and the compute node anymore. Okay, so that's the purpose of a burst buffer. Okay. In fact, most of the storage system or file system on a single node, we all know file system have buffer as well. You will buffer data during I/O for the same reason, but it's just in the scale of a single node. But only until recently, people start to realize they need exactly same mechanism at the computer system level, at the cluster level. So you have to install those nodes, acting like the buffer to bridge the gap between the storage device and the compute system. Okay, so this is what we call the burst buffer. Okay, all right. So all those are, as you can see, there are many interesting techniques happening in order to keep keep driving up the performance of our computer system. But in this lecture, we just introduce a few, so you can know what's could be or what's outside there. All right, so this is all for today's lecture, and on Thursday we will quickly finish this chapter and introduce our first programming language, MPI. If you have any question, feel free to unmute yourself. If not, feel free to log off now.